Hey guys, Mr. C here. We're going to do a little talk about the gravitational field. This is going to build on our last talk with Newton's law of universal gravitation. So, today's objectives. We're going to relate Newton's law of universal gravitation to Newton's second law in order to solve for the gravity of a planet. We're also going to calculate the gravity of an unknown planet given its mass and its size. Alright, so let's go ahead and jump right in. So, from last class, we learned about Newton's law of universal gravitation, and we learned that the gravitational force, F sub g, equals big capital G, which is Newton's gravitational constant, times the mass of the first body, times the mass of the second body in contact, divided by the straight line distance between them. So, Fg equals g m1 m2 over r squared. And then I've written over here what the value of g is that we're going to use for our calculations. What we're going to extend on today is, how can we relate this gravity to an acceleration? So what I'm going to do is I'm going to talk down here, what do we feel as the gravitational force? So when you're being pulled down, so for example, we have a little guy right here being pulled down by a gravitational field that's pulling him down, what is it that he feels? Well, if he's being pulled down by a gravitational force, what the man on Earth feels is his weight. So what we're going to do is, if we're going to observe a gravitational force happening to us, the way we feel it is by our weight. So in order to calculate the gravity of a planet, we're going to use our weight to help us find the gravity. So what I'm going to do is, I'm going to set the gravitational force, Fg, equal to the weight. What that means in terms of our equations is this. We're going to have our original equation, g m1 m2 over r squared, and we're going to set that to the equation for weight, and the equation for weight is just mg. And I'm going to call it m2 because I'm going to say m2, use different colored ink, I'm going to call m2 me, and I'm going to call m1 whatever the planet is. So again, m2 over here is me. And then because we're talking about a radius, we're talking about the straight line distance between the center of mass, so namely the center of a planet, and wherever we are. So if we're on the surface of a planet, this is just going to be the radius of a planet. All right. Now what I want to do is I want to work with that equation, and I want to solve for g, the gravity of a planet. So I'm going to go down here to the bottom and work in green ink, and if I put my g on the left hand side now, you'll notice that the m2's are on the numerator on both sides. So what it means is, it doesn't matter what the mass of me is or what the mass of the person is. The mass is kind of irrelevant actually. So if I cancel those two out, what I get is g equals big G times the mass of the planet, m1, divided by the radius of the planet squared. And there we have it. We've derived an equation to solve for the gravity of a planet as a function of its mass and of its radius squared. So, if we're given the mass and the radius of a planet, we can solve for the gravity on that planet. So for example, if we were given the mass and the radius of the moon, we could solve for the gravity of the moon. Or if we were given the mass and gravity of planet Vulcan, we could solve for the gravity of Vulcan. So let's go ahead and do this problem. Planet Vulcan has a mass of 5 times 10 to the 25th kilograms and a radius of 1.3 times 10 to the 7 meters. We want to know is, what is the acceleration due to gravity on Vulcan? Namely, we want to solve for what is gravity on Vulcan. So again, I'm going to label what we know. M equals 5.0 times 10 to the 25th kilograms, and the R equals 1.3 times 10 to the 7th meters. And we're going to go ahead and we're going to write down our equation. So I'll write that in black ink. G equals Newton's gravitational constant times mass of the planet divided by r squared. And I'm going to go ahead and plug in my values. So for G, I get 6.67 times 10 to the negative 11. For my M, that's 5 times 10 to the 25th kilograms. And for my R, That's 1.3 times 10 to the 7th meters. And please don't forget to square that term. So I'll give you a second to go through the calculations. If you need to, go ahead and pause. Okay, and when you're all said and done, you should get a value of G equals 19.7 meters per second squared. So about roughly 20 meters per second squared, which compared to Earth is about twice the gravity. So Vulcan have twice the gravity of that on Earth. So quick example, a person on Vulcan would feel twice as heavy as he or she would feel on Earth. All right. Well, that's the lesson on gravitational fields. I hope now you'll be able to solve for the gravity of a planet and also solve for the weight of a person on a planet using the gravity equation. All right, hope this helps. I'll see you guys in the next lesson.